Pluto has always held a special place in our imagination. For decades, it was just a tiny, faint dot of light in our most powerful telescopes, a mysterious world at the edge of our solar system. We knew so little about it, which only made it more fascinating. Its great distance meant that it guarded its secrets well, leaving us to wonder about its mountains, its plains, and its sky. This tiny world, smaller than our own moon, represented the frontier of exploration. It was the last major body in the classical solar system that we had yet to visit, a final distant shore waiting for a visitor from Earth. Then, in 2006, its status changed. Scientists reclassified Pluto as a dwarf planet. This decision sparked a great deal of debate among the public and astronomers alike. But this change in name did not diminish its scientific importance. In fact, it made Pluto even more intriguing. It became the most famous member of a whole new class of objects in the Kuiper Belt, a vast ring of icy bodies orbiting the Sun beyond Neptune. Understanding Pluto meant we could begin to understand this vast, unexplored region of our cosmic neighborhood, a relic from the formation of the solar system itself. Its journey from a distant point of light to a fully realized world began in earnest in July 2015. NASA's New Horizons spacecraft flew past Pluto, giving humanity its first close-up look at this remote and frozen world. The images it sent back were simply breathtaking. We saw towering mountains of water ice, vast plains of frozen nitrogen, and a surprisingly complex and active surface. The most iconic feature was a giant heart-shaped glacier named Tombor Regio. This single flyby transformed our understanding and showed us that even in the coldest, darkest reaches of the solar system, worlds can be dynamic and beautiful. Even after that historic encounter, Pluto continues to surprise us. The data from New Horizons, combined with new observations from powerful instruments like the James Webb Space Telescope, is painting an even richer picture. Recent discoveries have revealed a climate system so unique, it challenges our fundamental ideas about how planetary atmospheres work. It seems that this small, icy world, orbiting billions of miles from the warmth of our sun, still has many profound secrets to share with us. Secrets that connect to other worlds, and even to the origins of life on our own planet. One of the most stunning images from the New Horizons flyby was captured as the spacecraft looked back at Pluto. The Sun, positioned behind the dwarf planet, backlit its thin atmosphere, revealing something utterly unexpected and beautiful. Multiple layers of a vibrant blue haze. This ethereal glow extended high above the surface, reaching over 185 miles, or 300 kilometers, into space. It was a mesmerizing sight, a delicate blue halo surrounding a world of ice and rock. This discovery was shocking because scientists had not anticipated such a complex and extensive atmospheric structure on a world so small and so cold. This haze is not like the familiar haze we might see on Earth, which is typically composed of water droplets or dust. Pluto's haze is made of something much more exotic. It consists of tiny solid particles, which are believed to be complex organic molecules. These particles are incredibly small, likely similar in size to the particles found in smoke. Their presence creates a beautiful visual effect. They scatter sunlight in a specific way, much like the molecules in Earth's atmosphere scatter light. Because they scatter blue light more effectively than other colors, the haze appears blue to our eyes, creating a serene and otherworldly twilight. The initial observations from New Horizons gave us a snapshot, a single moment in time. But to understand how this haze behaves and what it does, we needed to watch it over a longer period. This is where the James Webb Space Telescope came in. Using its powerful infrared vision, JWST could study the temperature and composition of Pluto's atmosphere with incredible precision. The recent findings, published in June 2025, have confirmed that this blue haze is not just a pretty feature. It is the central component of a bizarre and unique climate system, one that actively regulates the temperature of the entire world. What makes this discovery so significant is that it presents a new way for a planet to control its climate. On Earth, our climate is primarily regulated by gases in the atmosphere, like carbon dioxide and water vapor, which trap heat through the greenhouse effect. On Pluto, however, it appears that this haze of solid particles is the main driver. This finding, confirmed by JWST's detailed observations, forces us to rethink our models of planetary climates. It suggests that even in the deep freeze of the outer solar system, complex environmental systems can form, governed by processes we are only just beginning to understand. To understand Pluto's unique climate, we must first understand the particles that make up its blue haze. These particles are known as tholins. This is not a specific chemical name, but rather a general term for a wide range of complex organic molecules that are formed when simple compounds are exposed to ultraviolet radiation. On Pluto, the process begins high in its thin atmosphere. The sun's ultraviolet light, even though it is faint at such a great distance, is energetic enough to break apart molecules of methane and nitrogen, which are the main components of Pluto's air. Once these molecules are broken into smaller, reactive fragments, they start to recombine in new and more complex ways. This chemical reaction, driven by sunlight, builds larger and larger molecules. It is a slow but steady process. Over time, these newly formed organic molecules grow, eventually becoming heavy enough to form tiny solid particles. These are the tholins. They are sticky, reddish-brown in their solid form, and are responsible for some of the dark, colourful stains we see on Pluto's surface. In the atmosphere, however, their tiny size allows them to scatter blue light, creating the haze we observe. The formation of tholins is not unique to Pluto. We see evidence of similar processes on other worlds in the outer solar system. Saturn's largest moon, Titan, is famously shrouded in a thick orange smog of organic haze, which is also made of tholins. Neptune's moon Triton, which many scientists believe is a captured cousin of Pluto, also has a thin, hazy atmosphere. What is remarkable about Pluto is how these tholins are not just a byproduct of atmospheric chemistry, but the very engine of its climate system, a role we have not definitively seen anywhere else before. This process has profound implications. The fact that complex organic molecules can be created so readily in the cold, distant environment of the Kuiper Belt is fascinating. These tholins are rich in carbon, nitrogen, and hydrogen, the fundamental building blocks of life as we know it. While there is no suggestion of life on Pluto, the natural production of these prebiotic molecules in such abundance shows that the raw materials for life can be found throughout the cosmos. Pluto's hazy sky is, in a way, a giant chemical factory, slowly creating complex matter from simple ingredients. For years, scientific models of Pluto's atmosphere predicted a certain temperature profile. Based on the amount of sunlight it receives and the gases present, its upper atmosphere should have been warmer. However, when New Horizons measured the temperature, it found something perplexing. Pluto's atmosphere was much colder than expected, about 30 degrees colder than the models suggested. The temperature was a frigid -333 degrees Fahrenheit, or -203 degrees Celsius. This discrepancy was a major puzzle. Something was actively cooling the atmosphere, but scientists weren't sure what it was. A hypothesis was proposed in 2017. The haze was the culprit. The latest observations from the James Webb Space Telescope have now confirmed this incredible idea. The tholin particles in the haze are the key to this cooling mechanism. During Pluto's long day, which lasts for about 6.4 Earth days, These tiny particles are very effective at absorbing the faint but energetic ultraviolet and visible light from the sun. This absorption process gently heats the haze particles. However, the story does not end there. The particles then release this absorbed energy back into space, but not as visible light. Instead, they radiate it away as infrared radiation, which is essentially heat. This process creates a strange kind of anti-greenhouse effect. On Earth, greenhouse gases trap infrared radiation, warming the planet. On Pluto, the haze particles do the opposite. They take in higher energy sunlight and efficiently radiate lower energy heat back into the cold vacuum of space, effectively acting as a planet-wide radiator. This constant release of heat energy into space is what chills Pluto's upper atmosphere, making it significantly colder than it would otherwise be. It is a beautifully simple mechanism, but one that had never been confirmed on a planetary body before this discovery. This climate system, regulated by solid particles instead of gases, is a first in our solar system. It forces us to broaden our definition of what a climate can be. It shows that even a world with a very thin atmosphere, less than 1/100,000th the pressure of Earth's, can have a complex and powerful system for distributing and radiating energy. Pluto's haze acts like a global thermostat, but one that is set to cool. This discovery highlights the amazing diversity of planetary processes and reminds us that the universe is often more creative and surprising than our models predict. Section 5. JWST, the eye that revealed the unexpected. Now, confirming that Pluto's haze was responsible for its cold atmospheric temperatures was honestly a significant challenge for astronomers. The New Horizons spacecraft, well, it provided the initial clues, but its fast flyby meant it could only gather data for, a very short time. To truly understand the climate, we needed an observatory that could, stare at Pluto for longer and see it in a way no other telescope could. This is where NASA's James Webb Space Telescope, or JWST, became essential. Launched in 2021, JWST is, indeed, the most powerful space telescope ever built, with an unparalleled ability to detect infrared light. This infrared capability was actually crucial. All objects that have heat emit infrared radiation, and by studying this radiation, we can measure their temperature. Pluto is incredibly cold, so the infrared light it emits is, very faint. The biggest problem, however, was its proximity to its largest moon, Charon. From Earth, and even from the vantage point of most space telescopes, Pluto and Charon appear very close together. Their faint heat signatures would, blend together, making it impossible to isolate the thermal emissions from Pluto's thin atmosphere alone. This technical hurdle had, prevented a definitive answer for years. JWST's incredible resolution solved this problem. Its giant mirror and sophisticated instruments allowed it to, finally, clearly separate the light coming from Pluto from the light coming from Charon. For the first time, astronomers could isolate the faint infrared glow of Pluto's atmosphere itself. This allowed them to create a detailed temperature map and see precisely how the haze was behaving. The data, collected through 2024 and 2025, confirmed that the haze particles were indeed radiating heat into space, exactly as the 2017 hypothesis had predicted. Without JWST's sharp vision, this mystery might have remained unsolved. The success of these observations highlights the power of combining different missions and technologies. New Horizons gave us the close-up, ground truth data from its flyby, revealing the haze and the temperature anomaly in the first place. JWST then provided the long-term, high-resolution follow-up from afar, allowing scientists to test their hypotheses and confirm the mechanism at work. This synergy between a daring flyby mission and a powerful orbital observatory is, truly, a perfect example of how modern space exploration works. Together, they have unlocked one of Pluto's most profound secrets. While Pluto was revealing its atmospheric secrets, its largest moon, Charon, was offering up some surprises of its own. Charon is a massive moon, about half the diameter of Pluto itself. The two are often considered a binary system, locked in a gravitational dance as they orbit a common point in space. For a long time, Charon was thought to be a geologically dead world, just a simple ball of ice and rock that was frozen solid. However, new observations from JWST in late 2024 have shown that Charon is far more chemically active than anyone had imagined. Using its sensitive spectrometers, JWST detected the clear signatures of two important molecules on Charon's surface, carbon dioxide and, even more surprisingly, hydrogen peroxide. The presence of carbon dioxide is interesting because it is believed to have come from Charon's interior. Scientists think that ancient impacts on the moon's surface may have fractured the crust, allowing carbon dioxide that was trapped beneath the surface to escape and freeze onto the ground. This suggests that Charon's interior may be more complex and differentiated than previously thought, perhaps with distinct layers of different materials. The discovery of hydrogen peroxide is even more startling. Hydrogen peroxide is a highly reactive molecule, and it does not last long on a planetary surface exposed to the harsh radiation of space. Its presence means that it must be continuously created. The leading theory is that intense radiation from the sun and from charged particles in space is constantly bombarding the water ice that covers much of Charon's surface. This radiation breaks apart the water molecules, and the resulting fragments can then recombine to form new molecules, including hydrogen peroxide. This is evidence of ongoing chemical reactions happening right now. These findings completely change our view of Charon. It is not a static, inert moon. It is a world where chemistry is actively taking place, driven by the constant interplay between surface ice and space radiation. The fact that we are seeing evidence of material from its interior and ongoing surface chemistry suggests that Charon has a more dynamic history and present than we ever gave it credit for. It has its own story to tell, one that is deeply connected to Pluto's but also uniquely its own. It is a reminder that even the most seemingly simple worlds can hide complex secrets. The discoveries on Pluto and Charon, when viewed together, tell a fascinating story of two interconnected worlds. They are more than just a planet and its moon. They are a binary pair, locked in a tidal embrace. They both orbit a point in space, called the barycenter, that lies between them. This means they perpetually face each other as they circle this invisible point, like two dancers holding hands. This close relationship has shaped the evolution of both bodies. For example, some of the methane that escapes from Pluto's atmosphere is thought to be captured by Charon's gravity. This captured methane is believed to be the source of Charon's most distinctive feature, its dark reddish north pole, nicknamed Mordor Macula. During the long cold winter at Charon's pole, the captured methane freezes onto the surface. Then, as the pole turns back towards the sun centuries later, the faint ultraviolet light triggers chemical reactions, converting the frozen methane into the complex, dark red tholins. This is the same type of material that forms Pluto's atmospheric haze, but here it is, painted directly onto the surface of its moon. It is a beautiful example of material being exchanged between two worlds. The contrast between the two bodies is also striking. Pluto has a thin but dynamic atmosphere that drives a global climate, and its surface is constantly being renewed by flowing glaciers of nitrogen ice. This makes its surface look remarkably young, with very few craters in areas like the heart-shaped Tombor Regio. Charon, on the other hand, has no significant atmosphere to speak of. Its surface is older, more heavily cratered, and covered in water ice as hard as rock. Yet, as we have now learned, its surface is not idle. It is a place of active chemistry, creating exotic molecules like hydrogen peroxide. Studying them together gives us a unique, natural laboratory. We have two worlds of similar composition, formed in the same region of the solar system, and orbiting each other closely. Yet they have evolved in vastly different ways. One has an atmosphere and active geology driven by volatile ices like nitrogen, while the other is an airless world dominated by water ice and radiation chemistry. By comparing and contrasting Pluto and Charon, scientists can better understand what factors allow a small, cold world to retain an atmosphere and what processes shape the surfaces of airless bodies in the outer solar system. The discovery of a haze-driven climate on Pluto does not just rewrite our understanding of this one dwarf planet. It provides a vital new perspective for studying other hazy worlds across the solar system and beyond. The most obvious comparison is Saturn's moon Titan. Titan is enveloped in a thick orange haze of tholins, much denser than Pluto's. For a long time, scientists have studied Titan's haze and its role in the moon's chemistry and climate. The new findings from Pluto provide the first confirmation of a world where haze is the primary driver of the climate system, offering a simpler model that could help us decode the more complex processes on Titan. By studying Pluto's climate, we can gain insights into how tholin hazes affect temperature, absorb sunlight, and influence atmospheric dynamics in a fundamental way. This knowledge can then be applied to our models of Titan, helping us better understand its own unique environment, which includes methane rain, rivers, and lakes. Furthermore, Neptune's moon Triton, which is widely believed to be a captured Kuiper belt object like Pluto, also has a thin nitrogen atmosphere with faint hazes. Pluto's climate system may be a near-perfect analogue for Triton's, giving us clues about a world we have not visited since the Voyager 2 flyby in 1989. Perhaps the most thought-provoking connection is to our own planet. Some scientists have proposed that early Earth, billions of years ago before life filled the atmosphere with oxygen, may have had a similar haze of organic molecules. At that time, the Sun was younger and fainter than it is today. A tholin-rich haze in the early atmosphere could have played a crucial role. Like on Pluto, it might have absorbed harmful ultraviolet radiation, protecting the fragile molecules on the surface. It could have also helped to stabilize the climate, potentially creating a more stable environment for life to emerge. While this is still a hypothesis, the discovery on Pluto provides real-world evidence that such a mechanism is possible. It shows that organic hazes can form naturally and have powerful climatic effects. Pluto, in this sense, could be a window into the distant past of our own world. By studying the chemistry and climate of this small, icy body, we are not just learning about the outer solar system. We are also gathering clues that could help us piece together the story of how our own planet became a habitable world and how life itself may have gotten its start. The continuing stream of discoveries from Pluto and its system is a testament to the enduring value of space exploration. The New Horizons mission, which gave us our first glimpse, is a perfect example. Even a decade after its historic flyby on July 14, 2015, the data it collected is still yielding profound new insights when combined with new technologies like JWST. The spacecraft itself is now venturing even deeper into the cosmos, heading towards the boundary where the Sun's influence ends and interstellar space begins. Its journey is far from over, and it will continue to collect data on this unexplored region for decades to come. These findings make a powerful case for returning to the outer solar system. The New Horizons flyby was just a snapshot in time. To truly understand the seasons on Pluto, which take 248 Earth years to complete one cycle, we would need an orbiter. A mission that could go into orbit around Pluto would allow us to watch its atmosphere change over many years. We could observe how the nitrogen glaciers flow and how the haze builds up and dissipates as Pluto moves closer to and farther from the Sun. Such a mission would answer questions that a single flyby simply cannot. The discoveries on Charon also beckon us to return. An orbiter could map its surface in high detail, helping us understand the source of the carbon dioxide and the full extent of the radiation-driven chemistry. We could even imagine a lander, one that could touch down on Pluto's heart-shaped glacier or near the strange red pole of Charon. Such a mission could analyze the surface materials directly, searching for more complex organic molecules and giving us an unprecedented look at the building blocks of life being formed in this cold, distant realm. These are ambitious goals, but they are the logical next steps. What Pluto teaches us, above all, is that the solar system is full of surprises. It reminds us that every world has a story, and that even the smallest, coldest, and most distant objects can hold clues to some of the biggest questions in science. From Pluto's haze-driven climate to Charon's active chemistry, these discoveries are expanding our understanding of how worlds work. They inspire us to keep exploring, to keep pushing the boundaries of our knowledge, and to continue our journey to understand our place in the cosmos. The heart of the Kuiper Belt has been revealed, and it is more dynamic and wonderful than we ever dared to imagine.